Good morning everyone. We are the Group 1 and our topic for today is Foundation. Introduction. In engineering, a foundation is the element of a structure which connects it to the ground and transfers loads from the structure to the ground. Foundations are generally considered either shallow or deep. Foundation engineering is the application of soil mechanics and rock mechanics in the design of foundation elements of structures. It is advisable to know the suitability of each type of foundation before their selection in any construction project. So, foundation is one of the essential parts of the structure. It is defined as that part of the structure that transfers the loads from the structure constructed on it, as well as its weight over a large area of soil, in such a way that the amount does not exceed the ultimate bearing capacity of the soil, and the settlement of the whole structure remains within a tolerable limit. Foundation is the part of the structure on which the building stands, the solid ground on which it rests, known as foundation bed. There are very wide range of foundation types suitable for different applications, depending on consideration such as the nature of the load requiring support, ground conditions, the presence of water, space availability, accessibility, and sensitivity, noise, and vibration. Okay, why a foundation is provided? Foundation should fulfill the following objectives. 1. Distribute the weight of the structure over a large area of soil. 2. Avoid unequal settlement. And 3. Prevent the lateral movement of the structure. And last, 5. Increase the structural stability. And why there are different types of footing? As we all know, there are numerous types of soil, and each type of soil has varied bearing capacity. Engineers chose several types of foundation based on the soil profile and load of the structure. So, in this lesson, we cover the most common types of foundation and examples of each. We also provide a visual evidence of each foundation to help clarify the benefits of each type of foundation.
Next is the function of the foundation. Safety and stability of a building depends upon the quality of foundation. It should transmit the dead and imposed loads to the subsoil uniformly so that the pressure on it will not cause settlement that can weaken the stability of the building. The foundation should be located in such a way that its performance will not be affected in the long run due to any unexpected internal and external influences and factors. In order to safeguard the building against damage or distress that can be caused by various factors, the foundation serves the following purposes. First, reduction of load intensity. Foundation distribute the loads of the superstructure to a larger area so that the intensity of the load at its base does not exceed the safe bearing capacity of the subsoil. Second, even distribution of load. Foundation distributes the non-uniform load of superstructure evenly to the subsoil. For example, two columns carrying unequal loads can have a combined footing which may transmit the load to subsoil evenly with uniform soil pressure. Due to this, unequal differential settlements are minimized. Third, provision of level surface. Foundation provide leveled and hard surface over which the superstructure can be built. Fourth, lateral stability. Foundation anchors the superstructure to the ground, thus impacting lateral stability to the superstructure. The stability of the building against sliding and overturning due to horizontal forces is increased due to foundation. Fifth, safety against undermining. Foundation provides the structural safety against undermining or scarring due to burrowing animals and flood water. 6. Protection against soil movements. Special foundations measures prevent or minimize the stress or cracks in the superstructure due to expansion or contraction of the subsoil because of moisture movements in some problematic soil.
To distribute weight over larger base are within safe bearing capacity. We can explain this as the bearing strength characteristics of foundation soil must be considered as significant design parameters in civil engineering structures. The amount of soil in place has a strong impact on how much pressure is placed on the soil. Bearing capacity is the maximum average contact pressure between the foundation and the soil, which should not produce shear failure in the soil, as load support capacity depends on the area of contact. In order to avoid failure, we need to increase the contact area. We accomplish this by spreading out the contact area to provide more surface area for a distributing load. A uniformly loaded foundation can be subjected to differential settlement, which is also known as differential settlement, which can occur due to soil having weak bearing capacity. Number 2 is evenly loaded state that prevents uneven settlement. Foundation may be subjected to differential settlement, which is called differential settlement. This may be due to a variety of factors such as subsoil conditions that affect bearing capacity, compacted soil with variable moisture content, and consolidated soil that has change in moisture content. So long as all other factors stay constant, we can divide the load evenly on the foundation to avoid differential settlement. When the structure is subjected to differential settlement, it results in structural damage or failure. Therefore, in order to avoid differential or unequal settlement, it is recommended that a structure be constructed without any differential settlement elements. Also, when considering the design of the structure, it is very important to distribute the load evenly over the foundation, so that settlement of the foundation will be equally. And lastly, deep enough preventing overturning and increasing stability. We can explain this as stable enough to remain upright and deep enough to ensure that it won't flip over. This is because the structure does not have enough strength to withstand the external load, which means the structure will fail, and this will happen when the foundation does not have enough strength to sustain the external weight. If the foundation does not have the capacity to withstand external load, it will fall over, which could cause the entire structure to collapse. To make the foundation more sturdy in order to ward off rolling or overturning are techniques that improve the stability of the foundation. If the depth of the foundation is greater than the contact area in between the foundation and the soil, then the frictional resistance against overturn will increase as well. In order to allow for more substantial depth of foundation, the frictional resistance must be increased.
There are two main types of foundation: the shallow foundation and deep foundation. We will further understand what these two are and what are under these two in the following slides. Shallow foundation is defined as depth of foundation is less than or equal to width. It transfers the superimposed load to the soil at a level close to the lowest floor of the building. Now, the first type of shallow foundation is spread footing or pad footing. Spread concentrated load by pillars or columns used for ordinary buildings. It simply is an evenly flattened surface which is spread to an area covered that are able to withstand the load in the pillars or column. It is most likely seen in an ordinary building or in residential projects, as you can see in the figure. Second is wall footing, a continuous strip of concrete that serves to spread the weight of load-bearing wall across an area of soil. It is somewhat it is actually similar to the first one, but the difference is that wall footing is for walls, as the name suggests. The load applied on the foundation wall will be transmitted to the covered area of soil under the footing. As the wall extends, the longer the footing is, as shown in the picture. The third one is step footing or step foundation. A footing in which the desired width is secured by a series of steps in about the proportion of 1 unit of horizontal dimension to 2 units of vertical dimension. This is applied on a slope area, as you can see in the picture, because the ground is not always smooth and flat. It is sometimes sloped. It is very difficult to construct house foundation on a slope. Following the slope with the foundation will not evenly spread the load to the soil, as it will only slide, no resistance at all. But step foundation will keep the footing on a level because it is stepped, flattening and evenly spreading the load on the area of the soil.
Slope footing are trapezoidal footings. They are designed and constructed with great care to see the top of the slope 45 degree is maintained from all sides. This type of footing is usually used to distribute load evenly from columns to the soil, to transfer the load of the column to its base evenly. That's why we provided the slope pattern of the footing 45 degrees. For the strap footing is a combined footing with two or more footings, under a column of each, are joined together with a beam to form a single combined footing. Now, strap footing is usually used to help distribute the weight of either heavily or eccentrically loaded column footing to adjacent footings. It is used when the distance between two columns is so great that the combined trapezoidal footing becomes quite narrow with high bending moments. For the combined footing, a combined footing is a footing that has two or more columns that are located very near each other, that we provided a single substructure for them, and the footing is known as a combined footing. A combined footing is when the load-bearing capacity of the soil is low and when under the individual footing requires more area than a combined footing is construed. When the combined footing should be rectangular combined footing, trapezoidal combined footing, strap combined footing, and raft combined footing. In this combined footing, the maximum bending moment takes as the design value for the reinforced concrete footing. And lastly, for the shallow foundation, mat footing or raft footing spread across the entire area of the building to support heavily structural loads from columns and walls. This kind of footing is often used when the soil is weak, as it distributes the weight of the building over the entire area of the building and not over smaller zones or at individual points. So, that reduces the stress on the soil.
What is deep foundation? A deep foundation is a foundation that transmits the load of a structure of strong soil beds or rock beds available in great depth. When the soil at a near the ground surface is not capable of supporting a structure, deep foundations are required to transfer the load of deeper strata. Also, the depth of the foundation is very large in comparison to its width. It transfers the superposed load to the soil at the level that is a great distance from the lowest floor. There are different kinds of types of deep foundation. First is the pile foundation. Pile foundation These foundations are known as deep foundation. A pile is a slender column made of wood, concrete, or steel. A pile is either driven into soil or formed into situ by excavating a hole and then filling it with concrete. A group of piles are driven to the required depth and a capped with RCC slab, over which superstructure is built. A pile transfers the load to soil by friction or by direct bearing. In the latter case, piles being taken up into hard strata, this type of foundation is used when topsoil is not capable of taking the load of structure even at 3 to 4 meter depth. Pile foundations are classified according to material used and also on the nature of load transfer. Classification according to material use, pile may be classified as to four groups: timber piles, concrete piles, steel piles, and composite piles. The second one is well foundation. Well or cast-stone foundation is the type of foundation that is commonly used on roads, railways, and bridges. Such a foundation can be sunk to a great depth and can carry very heavy vertical and lateral loads. Well foundation can also be installed in a boulder stratum. Well foundation, it is the most common type of foundation in India for both road and railway bridges. It is relatively rigid in structural behavior. This is the well components, or this is some of well components: cutting edge, well curve, well staining, bottom plug, sand fill, top plug, and well cap.
So good day everyone, I'm Pauline Charlie Sideris and I'll be reporting the second part of types of deep foundation. So first we have here the basement foundation. Basement foundation, it is an architectural structure that basically secure a house or other building about a floor below the ground level. So we have an example here of basement foundation. As you can see dun sa gitna niya mayroong white space because depende kay owner or kay client kung gusto niya gamitin yan as working area or storage areas. Specifically sa west, ginagamit nila yung basement nila as relocation area because nakakaranas nga sila din ng tornado. So the next one, we have here buoyancy raft or hollow box foundation. These type of foundation are designed in such a way that they behave as buoyant structure for the net loading over it. So from the word itself, buoyant, it is the ability or tendency to float, meaning kapag nagkaroon ng flood condition or pagtaas ng tubig, si mismong structure is aangat din. So the last one is drilled shaft or pier, also referred to as a drilled pier or board piles, are used to support structure with large axial and lateral loads. So these are the example of drilled shaft. Ang advantage ni drilled shaft kay pile foundation is since nga drilled siya, hindi nakakaramdam si ground ng vibration. Unlike kasi kay pile foundation na pinupokpok, so nakakaramdam si ground ng vibration. Yun lang, thank you.
We also have to consider the foundation design and construction. First, footing defense spacing. This is a foundation that shall be designed in the bottom and it's located below first line. Then, the footing must be placed underneath the topsoil layer to prevent the soil from consolidating. Usually, the loosest type of soil is containing the organic material. Second, soil settlement. After the foundation installed, next step will be soil settlement. This time, the geotechnical should check the bearing of the soil to ensure that the loads will not cause negative effect in the soil to settle. Third, soil erosion. It also applies to bridges and walls. To avoid the erosion, the water are not allowed to flow in the bottom of the foundation. In that case, tile should be installed at the base of the foundation. Fourth, foundation in salt and silt. Before then, foundation sand and silt can be installed. This make the wind in the water to erode sand and silt to close the ground. Lastly, the foundation in loose and other collapsible soils. Collapsible soils are deposits of silts, sands, and volcanoes ash. Structural engineers need to consider certain condition of the load and wetness of the soil. In general, collapsible soils undergo sudden changes in volume and collapse when their moisture constants increase with or without loading. The picture in the left side represents structure before inundation and the right side represents the soil structure after the inundation.
Bearing capacity. The bearing capacity of a foundation is the maximum load that can be applied on a foundation to ensure that there would be no failure or uncontrolled deformations will occur. Engineers should ensure that they know the bearing capacity of a foundation so to avoid accidents due to a failure of an infrastructures. Also, to ensure that the infrastructures will last in the long run. These factors we need to consider in bearing capacity of a foundation. These are ultimate bearing capacity, maximum safe bearing capacity, and allowable bearing capacity. Ultimate bearing capacity. It is the value of a maximum pressure that can be supported without fail. The ultimate bearing capacity of a foundation denotes that the maximum load that the foundation soil can withstand, and reasonable determination of one of the pivotal parts in foundation designs. Maximum safe bearing capacity, on the other hand, it is the bearing capacity after applying of the factor of safety. There are two types of safe bearing capacity, safe net bearing capacity and safe gross capacity. The maximum intensity of loading that the soil will safely carry out without the risk of shear failure is called safe bearing capacity of the soil. It is obtained by the ultimate bearing capacity by a certain factor of safety which is used in the design of foundation. Meanwhile, allowable bearing capacity, it is the value of maximum bearing stress that can be applied to the foundation to make it safe against instability due to shear failure. The allowable bearing pressure is the soil's ability to carry the load of a building and its contents without excessive settlement. Few building Few building failures are caused by insufficient soil bearing capacity even when footings are unevenly loaded. This is because the load imposed on foundation soils by houses, even those with solid masonry walls, are small compared to the bearing potential of the natural firm soil.
Stages in the development of foundation failure. What is foundation failure? Foundation failure in the building can be attributed to several things. Most commonly, foundation failure is caused by the movement of expansive high plastic soil beneath different sections of the foundation footings. Common reasons of foundation failure: low bearing capacity of soil, improper compaction, poor construction, ground vibration, plumbing issues, improper drainage. Most commonly, foundation failure is caused by the movement of expansive and high plastic soil beneath different sections of the foundation footing. This movement of soil can be in the form of shrinkage, which cause settlement, or expansion, which cause heave. Early warning signs of foundation failure: crack, crumbling or compromised foundations, shifting soil and water damage, gap in walls or the foundation, drooping floors or warped ceilings, door or windows that don't fit.
Methods of improving bearing capacity. So these are the main methods that are commonly used in improving bearing capacity. Our first method is increasing depth formation. And in this method, it simply means that at deeper depths, the overburden pressure on soil is higher. Therefore, the soil is more compacted. Therefore, it shows higher bearing capacity. However, this is only applicable in cohesionless soils and not applicable if the subsoil material grows wetter as depth increases. And this method has a limited use because if the depth increases, the weight and cost of the foundation also increases. That's why it's limited. Our second method is draining the soil. In draining the soil, the presence of water decreases the bearing power of soil. Okay, that's why we need the water in soil to be collected and drained out. With increase in percentage of water content in soil, the bearing capacity decreases. And in our last method, compacting the soil. In compacting the soil, it resulted to the improvement of bearing capacity. This is one of our goal in order for us to have a higher bearing capacity. Is we need to have a compacted soil. If we compact soil using appropriate method, then there will be increase in its density and shear strength. And as a result, the bearing capacity of soil also increases. There are many methods in compacting soils. Some of these methods are by spreading broken stones, gravel, or sand. These are the hard materials that can cause the soil to be compacted. Some and the second method that we can use in compacting the soil is using an appropriate roller, and it depends to the specific type of soil. Because if you use an inappropriate roller, it can cause the soil to be destroyed, and which cause the bearing capacity to decrease. So if we want to improve our bearing capacity, we need to use an appropriate roller in compacting the soil. And lastly is by driving concrete piles or wood piles and withdrawing piles and subsequently filling the holes with sand or concrete. So in this method, we use sand or concrete in compacting the soil.
Geological hazard is an extreme natural event in the crust of the earth that pose a threat to life and property. For example, earthquakes, volcanic eruptions, tsunamis, and landslides. First, fault rupture. Geological site condition must be defined in sufficient detail to assess the potential for the trace of an active fault to be present in the building foundation soils. Second, liquefaction. Subsurface soil and groundwater conditions must be defined in sufficient detail to assess the potential for liquefiable materials to be present in the building foundation soils. If liquefiable soils are suspected to be present, the following information must be developed: soil type, soil density, depth of water table, ground surface slope and proximity of free face conditions, and lateral and vertical differential displacement. Lastly, is landsliding. Subsurface soil conditions must be defined in sufficient detail to assess the potential for a landslide to cause differential movement of the building foundation soils. The following slides shows the effect of geological hazard on the foundation of the building.